In this video, I will tell you about the interrupt in 8051 microcontroller. Interrupt are nothing but external or internal event that informs microcontroller that it require its service. There are two ways the microcontroller can serve the device. Two methods are one is interrupt and another one is polling. In case of polling, the microcontroller continuously monitor the status of given device. When the condition is met, it performs the service, and after that it move on to monitor the next device until everyone is served. And in case of interrupt, whenever any device need its service, the device notifies the microcontroller by sending it an interrupt signal. Upon receiving an interrupt signal, the microcontroller interrupt whatever it is doing and serve the device. The program which is associated with the interrupt is called interrupt service routine, or also known as interrupt handler. Let's see it graphically. So consider we have two devices. For these two devices we are using polling method, and these two devices we are using interrupt method. Suppose I have written logic like this: if I press a switch, either of the switch, the LED will turn on, and if I again disconnect the switch, the LED will go off. The same is about these two switches. So switches are here acting as an external event given to the microcontroller. So you can consider it as a external devices. So in case of polling method, when you write a code, you have to write a code where you will monitor the status of these two pins continuously. So these two conditions you will write under while one loop, where you are continuously checking the status of these two pin, and when the pin status go from high to low, that means the event is occurred. If I press a switch, I will give logic 0, that means interrupt, what we can say, the change in this logic of this pin will get captured by 8051 microcontroller. So this is what we call polling. We are continuously checking the status of these two pins in while one loop. Now in case of interrupt, here we are not monitoring the status of these two pins. 8051 microcontroller is performing its normal operation. Whenever there is a logic 0 or whenever there is an interrupt given to the 8051 microcontroller, 8051 microcontroller will stop its current execution of code, and it will go and execute the code written for this interrupt. That is what we call internal subroutine. That is what we call internal subroutine or interrupt handler. So whenever there is an interrupt, it will go to interrupt service routine, and that code will get performed. Okay. So this is what is the basic difference between polling and interrupt. In polling, we are continuously wasting the microcontroller time in checking the status of these two pins. Now here, in case of interrupt, we are not wasting the CPU time. Whenever there is an interrupt, it will go and serve the device and will come back and execute its own operations. So there is wastage of time, CPU time in polling, and there is no wastage of CPU time in interrupt. Interrupt vector table. There are total 6 interrupt possible in 8051 microcontroller: reset, external hardware interrupt, timer 0 interrupt, external hardware 1 interrupt, timer 1 interrupt, and serial communication interrupt. So there we have total 6 interrupt in 8051 microcontroller, out of which the external hardware interrupt 0, external hardware interrupt 1, these are external interrupt to 8051 microcontroller, and reset is also the external interrupt to microcontroller. Timer 0 interrupt, timer 1 interrupt, and serial port interrupts, these are the internal interrupt to 8051 microcontroller. Every interrupt is associated with one particular address in ROM location. For reset, it is always 000H location. For external interrupt 0, that is INT 0, 003. Similarly, for RINTI interrupt, the address is 0023H. All these values are in hexadecimal. Whenever this interrupt will occur, the hardware will automatically set logic 1 to this particular interrupt. Then, after servicing these interrupts, the microcontroller only will clear this flag, these interrupt flags. But for serial communication interrupt, the programmer has to clear the flag manually. I will tell you the difference when we will write the code. Okay, so this is what we call interrupt vector table. ROM memory locations 00 to 30H locations are for interrupt vector table. When the interrupt is evoked, the microcontroller runs the interrupt service routine. For every interrupt, there is a fixed memory location that holds the address of ISR. So whenever there is the external interrupt INT 0, the control will get transferred from the main code to the address 003H. And now from 003H address onwards, you have to write the subroutine code. So at this address, you will find your ISR. You have to write ISR, the interrupt service routine, from the address 003H location. The group of memory location set aside to hold the address of ISR is what we call interrupt vector table. Because of interrupt vector table, it is always advisable to write our code from 30H location onwards. To do this operation, what we do is we write the long jump instruction at the address 00H. This is because, and the main will get labeled to the location 30H, right? So this is we are doing because from the 002 to F, these locations are for interrupt vector table. I am simply bypassing those interrupt vector table by using long jump instruction. And why I have written this to 00H only? Because whenever we reset the microcontroller, by default, the program counter will point to the location 00H. That's why. So this would be the first instruction get executed by program counter. And hence we are simply bypassing the interrupt vector table by using this instruction. And we have to write our code from ORG 30H location onwards. So this is the best practice when you are using interrupt vector, whenever you are writing code for interrupt. If you are not writing code for interrupt, you can directly start writing your code from ORG 00H. Let's discuss about the interrupt and its working in assembly language in more detail. Suppose my task is I want to continuously blink the LED. I want to continuously generate one square wave on pin number 1.3. And whenever there is an interrupt, I want the LED status should change. If it is 1, if the interrupt occur, it should go 0. If it is 0, if interrupt occur, it should go 1. So this is my code for performing this operation. Continuously I am generating square wave. Whenever there is an interrupt, I want the change in the LED state. Okay. And these are the addresses for interrupt vector table. 00 for reset, 003H to 00AH is for INT 0. Suppose the microcontroller is currently executing this code, and now he is executing particularly this line of code, clear port 1.3. When the PC, the program counter, is pointing to this particular instruction, and if there is interrupt occur, the current instruction get executed completely by 8051 microcontroller, and the next instruction 0404, this instruction, this particular address will get stored to the stack memory. Then the PC will get shifted to location 003H. So simply the program control now is transferred from main code to the ISR, interrupt service routine. And you can see the ISR is present from the address 003H onwards. Because whenever there is the INT 0 interrupt, by default, the program will get transferred to ISR, to the address 003H location. That's why you have to write the subroutine code from the address 003H onwards. So now the transfer of control is to ISR. So here we have written these two instructions. So CPL is nothing but complement. Complement the status of port 1.4. If it is initially 0, it will become 1. If it is 1, it will become 0 after execution of this instruction. Then RETI, return from interrupt. So when this instruction get executed, the content in the stack memory will get pop up into the program counter. So now program counter contains 0404, and hence there is a transfer of control from interrupt subroutine to main code. So this is what is our return address. So now the microcontroller will continue executing the remaining code. So this is the working of interrupt in 8051 microcontroller. Now there is one register called interrupt enable register. This register is responsible for enabling and disabling the particular interrupt. EX0, external interrupt 0. If it is 1, then it is enabled. If it is 0, that means it is disabled. Similarly, true for timer 0 overflow interrupt, external interrupt 1, timer overflow interrupt 1. ES is for serial port interrupt, and ET2, it is timer 2 interrupt, which is present in 8052 microcontroller, not in 8051. And there is D7 bit EA, enable all. So when this bit is 1, that means all interrupts, all these interrupts are enabled. If it is 0, that means all interrupts are disabled. So we can call it as a master enable bit. So if I want to use INT 0, in that case, what should be the value? 1000. That means 80001. 81. So this value you have to load, right? So here 81, this hex value I have loaded to IE register to enable the INT 0 interrupt. So this is what is the use of interrupt enable register, simply used to enable the particular register. In 8051 microcontroller, we have two external hardware interrupt pins, INT 0 bar and INT 1 bar. Both these pins are active low pins. There are two types of activation for external hardware interrupt. One is level triggered, the another one is edge triggered. INT 0 and INT 1 pins are normally high pin. They are active low pins, but the status of this pin by default is logic high. Level triggered is the default mode upon reset of 8051 microcontroller. So by default, INT 0 and INT 1, the logic is 1. Now when I give it logic 0, constant logic 0, at this point the microcontroller will get triggered interrupt, level triggered interrupt. If you want to configure microcontroller for edge triggered interrupt, in that case if there is change in the logic to the pin from 1 to 0, now at this point whenever there is a transition, at this point the 8051 microcontroller will get interrupt. To configure microcontroller for edge triggered interrupt, you have to give logic 1 to bit number 0 for external interrupt 0 pin, and logic 1 to INT 1 bit number 2 for configuring INT 1 as a edge triggered interrupt. So these two bits are used to configure 8051 microcontroller either level triggered or edge triggered. If these two bits are 1, then level triggered interrupt is activated. If it is 0, if it is 1, edge triggered. If it is 0, level triggered interrupt. IE0 and IE1, these two bits are simply the interrupt monitor bit. Whenever there is an interrupt, these two bits will get set to logic 1. Whenever there is an edge interrupt, these two bits will get logic 1, and these two bits will get cleared out when the microcontroller come out from the subroutine. So mainly the bit number 0 and 2 is important to us.